Hello everyone, welcome back. So this is the last lecture of the course. So we were talking about the quantum light and we understood various aspects of it. So now what is it useful for? Okay. Well, aside from the actual, beauty of the science, there are some applications that people are really seriously looking at right now. Okay. So one of the primary reasons for looking at it is essentially if you think about the computing itself. Okay. We are in a regime where we call as classical computing, wherein we are dealing with zeros and ones. Okay. These are deterministic quantities. There's nothing, the voltage is precise, whatever you measure, correct? That's how the classical, the computers are working. But these work for very simple systems. Okay. If you want to build a logic gate, you can build it nicely. But the moment if you go to larger problems where you have many variables, for example, look at climate, rainfall. Okay, the rainfall depends on so many different parameters. And if you want to efficiently model it, right now we are using supercomputers. Okay. And let's say you want to simulate how, let's say, the brain works. There are these millions of neurons inside. They're all acting together. We understand how an individual neuron behaves, right? But we don't know how all of them together work. I mean, we can define some simple things like action potential and how the chemical, how the ions are actually moving across the membranes and so on. And that has implications, and we understand to some degree. But really, if you want to model a very complex system, we cannot do it right now because it's we still make some assumptions and then we solve it. Okay. Luckily for us, we saw that many cases, even if you have a complex phenomena, you make an approximation like a harmonic oscillator, you still can make a lot of progress. But, in reality, life is much more complex. Okay. So if you want to study that, the current, computational, there are limits. For example, even though you have the fastest supercomputer, it might take some simulations days and years and months and years to actually calculate it. So it's a hard problem. And the solution was actually proposed by Richard Feynman, I think in 1982. He was giving a talk and he was talking about how the computing is, and he said if you have an intrinsically complex system, okay, like the quantum, intrinsically everything is quantum, right? If you have such a complex system, you cannot use classical means to solve for it. If you try to model it using classical means, you will soon realize that the system is, the complexity of the computations becomes very hard, very high, and you can't solve it. So Feynman proposed that we need to build essentially a quantum hardware, not a classical hardware. Because if you build quantum hardware, you will see that in real life, as the size of the problem increases, it's becoming much more complex, right? And even the quantum hardware will scale. The capabilities of the hardware also will scale similarly. And so we have a chance of actually modeling complex systems. And that cannot be done using classical computing. You have to actually harness quantum hardware, basically. Okay. But nobody has yet built it. We are still in the early stages of it. Okay. But provided we build it, we can have a lot of impact. Okay. And all this, understanding of science is to get towards that. Now, if you look back in the electronics domain, I think some of you might know that the MOSFET was actually proposed in, late or early 2020s. Okay. But before it could actually be manufactured, it was first demonstrated in 1950s. So there was nearly a 30-year gap between the concept and the implementation. Okay. And even after that, there is a 40-50 year of evolution that actually enabled all of this. So we should not think about applications immediately, but over time, I think things progress. All right. And we already see that. Okay. So I'll try to explain the impact of quantum light using communications as an example. Okay. That's what, we'll try to understand. So right now we all are communicating, there is information that is being sent from your phone, from your computer to the servers and so on. Let's say with the bank servers, we want it to be secure. And the way we make it secure is by using what they call as RSA algorithm. Okay. RSA is the name of the algorithm, let's say. Okay, so what happens is, let me actually, just give me a minute. I'll copy this page and actually paste it. I'll repeat this so that I can have, yeah. So RSA algorithm is basically the protocol that we use, okay. What essentially is happening is, like, we all understand how a password works. If you encrypt something with a password, it is not possible to break it till you don't know the password, right? Now the question is, if you have a very powerful computer, nothing prevents me from actually scanning through. If I know it's an 8-letter password, I can scan through it and then I can, figure out, I can break a code, right? So if you want to make something secure, RSA protocol demands that you use what is known as public key encryption. Okay, they use what is known as public key encryption. What do I mean by that? Well, the idea is simple. Let's say I take two prime numbers. Okay, so there is a public and a private key. Okay, there is basically in RSA, RSA protocol has public key and a private key. Okay, let's say I want to send some information, rather you want to send me some information. I want to receive some information from you, but I want it to be secure. So what I will do is I will generate a private key. What essentially it consists of, let's say, two prime numbers. Okay, if I take two prime numbers and I multiply them and I'll give the product to everybody. I'll publicly announce the product. I won't tell you what those prime numbers are. For example, I'll take 7 into 11. That's a small prime number. Okay, for example, but in reality, we'll actually take large prime numbers. Okay, so that when you take the product and let's say I'll publicly announce that my public key is 77. Okay, for this example. So what you will do is you will take this number 77 and encrypt the data, whatever you want to send it to me, you will encrypt it with that public key. And once you do that, you will send it to everybody. But X, Y, Z, they don't know what the public key is, so they can't decrypt it. Okay, and that also can be only decrypted once I know the combination that I used. The product is known, but you don't know the prime factors that are there in that. So essentially, if you have to decrypt it, you should know what those prime numbers are. So the process of finding out the prime numbers can be decrypted using by factorization, basically by knowing prime factors. Okay, so if you have to know the prime factors, what would you do? In a classical computer, you will start with, let's say, if there is a number n, that's what you want to find out the factorization of that. You'll start with 0 or 1 and then keep going up to root of n and keep dividing the number with each number that is available to you and see if there is a remainder. If there's a remainder, then it is not the factor, right? So that's how you factorize. So now if I have a large prime number, the factorization becomes very, very complex. Okay, so basically in the computer science world, there is something called as polynomial and non-polynomial time, NP and P. Okay, so essentially if you look at a function, excuse me. There are some problems. If I look at my x-axis is the size of the problem, n, okay, size, okay, and my function f of n, basically. There are problems which actually go as polynomial time. That's what we call. So essentially what happens is the complexity of the problem increases as a polynomial. Okay, maybe something like n power 4 or n power 3 and so on. So that means if you increase the size of the problem, if I have a computer which actually has similar increase in the hardware, I can solve it. Okay, for example, somebody had a simple password, let's say 1960s. Today's cell phone can crack it because my complexity of the hardware has increased. So if I have a weak encryption, I can crack it with a powerful computer. But there are some types of problems which are actually, they are called, this is n power 4 is basically a polynomial time. This is polynomial time. Basically, it takes time as a polynomial. I know if the problem becomes slightly more complex, the solution becomes slightly more complex. Okay, that is a polynomial time problem. There's another class of problems which are called as NP, non-polynomial time. Okay, for example, exponential of n. If I have such a problem, what happens is essentially, as the size of the problem increases slightly, the complexity of the hardware required to solve it increases exponentially. Okay, so that is an NP problem. In the language of computer science, we call it NP. Okay, so one such example for that is prime number factorization. Prime number factorization. What do we mean by factorization? Well, essentially the constituent prime numbers. If I give you a product of prime numbers, what are the factors, prime factors? So it's an NP problem. That means if you increase the key length by, let's say, one bit, it exponentially increases the complexity. So now what we do is we use public keys which are like 256 bit or 512 bit and so on. So we are increasing the size of the encryption key. If you increase the size of the encryption key, it becomes nearly impossible for the computer to solve it, because even if you put a supercomputer, I'll always increase it from 512, I'll make it a 1024. Okay, so whenever we talk of security protocol, sometimes you see 128 encryption, 256 encryption, and so on. So if you have a large enough size, I'm just increasing the size of the key by twice. Like, that's all I'm doing. But the resources required to solve it increases exponentially. So even a supercomputer cannot crack it. Okay, that is a whole game of security protocols right now. Okay. Oh yeah, okay, yeah. I should not say it cannot crack it. It takes infinite time, or very, very long time. If it solves in 100 years, I don't need it. I mean, it's not useful to me. So because it's an NP problem, it's a non-polynomial problem. It's an exponentially increasing complexity, right? So that's how all the things are secure right now. Everything. There's no exception. Defense, whatever. It's all. Now the problem is, I was talking about the Feynman's approach. Feynman, he suggested that if you have a quantum computer, it should be able to solve complex problems. I mean, it is a fair general observation. It was just because the nature is complex, you need more complex. You can't just deal with classical zeros and ones and deal with it. Okay, so it was shown. I mean, yes, right now you work on zeros and ones, right? That's what is a bit for us. Binary digit or binary bit, right? So now instead of that, if you work on a quantum bit, qubit, okay, if you work on a quantum bit, qubit, what I can do is this. I can call it as a psi. Let's say some wave function in our language, quantum language. Instead of 0 and 1, I'll talk of a superposition of 0 and 1. Okay, C0 plus C1. I'll take these two bits and in addition to 0 and 1, I'll also take a superposition of it. For example, we talked about the mixture states, wherein you don't consider superposition. The probability of, let's say 0 will be C0 square, C1 will be, state 1 will be C1 square. But if you have a superposition, you can also have some exchange of, states, right? In the case of Rabi oscillations, we were talking about it. So similarly, if you have a superposition state, you can have actually more number of states available to encode. Okay. So if you have 2 bits, how many states will you have? 4. But if I have, or rather, with a quantum this thing, I can have even more superposition states, right? So, and the hardware required for that is not that, with just, with smaller amount of hardware, I can actually deal with more complexity. Okay. So if you do that, if you have such a qubit, now you might say, you can't measure it, right? It's all, it's in the quantum state of the matter, right? Whatever you're encoding, you can't read it. The moment you read it, it collapses to a certain state. But then intrinsically in the background, you can measure C0 square or C1 square and so on. You can determine the system. There's some probability to determine that. But then if you don't make a measurement, it evolves over time in its quantum state. And after it finishes evolution, you find out the solution, the probabilities. If you are able to encode your system as, if you prepare a system, quantum system in some state, let's say, and let it evolve in a particular potential or whatever, it gives you the solution. You don't need to, solve it. The nature itself will actually takes it in the proper direction. Okay, so these are what are known as quantum simulators and so on. Some people are working on it, and it's an interesting problem itself. But coming back to the context of this encryption, if you have a quantum computer, Peter Shor, a scientist by name Peter Shor, has shown in 1994 that you can factorize prime numbers in polynomial time. So basically, the prime number factorization was a NP problem, right? So if I'll just move this out here. So basically, the prime number factorization, this was NP problem in classical compute. But it's a P problem, polynomial time problem in quantum hardware. So he gave an algorithm for factorizing actually. So how are we doing on time? How much time we did spend? 10 minutes. 17 minutes. Oh, wow. Okay. I didn't realize. Okay. So basically, anyway, it's interesting, right? So you have polynomial time problem like this. So now that means all the encryption that we have done is now done. It's useless. You can decrypt. Now, there are already primitive quantum computers that people are building. For example, Google is building something, D-Wave is building something, IBM is building something. These are few bits. It's not anything comparable to what we have classically, but they still can already solve some real problems. Okay, you can actually, there are things like, there are some services through which you can actually access Amazon's supercomputer, not quantum computer, and run some simple gates on that. There are toolkits, syskit and things like that. Some interesting things are there. Okay. So you have some things which can actually help you solve the quantum problems. So what if the quantum computer becomes a reality? Now that has given, a lot of, it made all the governments nervous. They're investing heavily into figuring out what is the post-quantum protocols, encryption. So that we have to build new security protocols because everybody wants to save their secrets. Especially governments want to save their secrets. Militaries want to save their secrets. So how do we build hardware or encryption protocols which are post-quantum? Okay, in that context, already there are actually commercial products that are available that can actually withstand even a quantum computer. Okay, and that is one application that people are looking at right now. Okay, so what is that? Well, to actually cut the long story short, we talked about this issue of encryption, right? So now what's happening physically is when you transmit information, let's say you're transmitting some information to me, you're essentially sending it as a basically zeros and ones, right? It's light pulses. So in the language of cryptography, it's conventional to use terms Alice and Bob. Alice is a transmitter and TX transmitter, Bob is a receiver, and Eve is basically an eavesdropper. So basically somebody is trying to listen into the information. So now if you send the information in the classical approach, for example, Eve, like let's say you're sending 100 photons here, not 100, maybe 100 million photons you're sending. Okay. And Eve can easily take half of it, put a beam splitter here. Let's, for example, here, 100 million photons. You can take 50 million photons from here, read from a beam splitter, and then send out 50 million photons forward, and then put an amplifier, gain 2. If I do that, so essentially I'll get back 100 million photons. So Alice and Bob will not know that somebody has actually interfered with the system and actually listened into the conversation or the data. So basically you can read the data, and it's a breach of privacy, right? Or rather breach of security. So this encryption is not really secure. Okay, whatever you do, you can always read it, right? So now to withstand against that, what scientists are proposing is actually to use quantum light sources or quantum, keys. Okay, so basically, if you have such people who are withstand, you are actually, instead of classical light, right? Let's say classical light means, let's say 1 milliwatt of light has 10 power 15 photons per second. Correct. Instead of that, I will use quantum light source, which has maybe 1 photon quantum light. I'll send a number state. I'll send a quantum light as, let's say, 1 photon per pulse or something like that. So if I have very few photons, let's say I'll go to even 0.1 photon per pulse. So essentially I'm sending zeros and ones as pulses. If I don't send a pulse, it's a 0. If I send a pulse, it's 1. So I'll actually send very, very few photons in the pulse. If I'm able to do that, what will happen? It's a quantum state. And basically the theory, quantum theory tells us that if you have a quantum state and Eve tries to measure the quantum state, then automatically the quantum state gets disturbed. And Bob and Alice will get to know that somebody had tried to read it. So they can discard that and again send one more. Okay, this is a whole idea of it. And for that, there are multiple things that are, important. Basically, you need a hardware that is capable of sending that. You also need quantum, basically random numbers. A truly secure thing is not really anything deterministic, whichever follows an algorithm that is not secure. Let it be RSA. RSA also is effectively an algorithm. Only the guesses are different. But what those guesses are, you can't, a human being cannot sit and keep guessing numbers, right, randomly. Even if a human being does it, there is some sort of pattern to it eventually. Okay, the way the mind works also, there will be some sort of pseudo randomness introduced. If you write any code, let's say, in MATLAB or Python, you write random number generations, random numbers, right? They are still again, same. They are not truly random. They are what are known as pseudo random numbers. So we need a truly random number generation source. So quantum random number generator, let's say QRNG. If you have a QRNG, it will truly generate a random number. There could be many processes that can create it. For example, spontaneous emission. We said spontaneous emission is simply a photon emission stimulated by vacuum state. Okay, that is random, truly random intrinsically. Or, maybe, radioactive decay. Or, many different things like that. Truly random phenomena, if you take, you can have quantum random number generation. And then with that, I encode my data and I can send it. So then if I'm able to do that, and if I use quantum light to transmit, okay, generation is one aspect, and then quantum keys have to be distributed. You somehow manage to generate using a quantum random number generator, but then that also has to be transmitted. And for that, we need this key distribution, what we call as QKD, quantum key distribution. And this is one of the most, near-term technologies which has matured. Computing is still a bit far away, but quantum communications is already coming into, some sort of a shape, reality. Okay, there are a lot of companies now that they're trying to push it and so on. So there's a lot of interesting work that's going on. All right. So how do we do this quantum key distribution? Okay. Previously, it was, so first of all, how do we generate a, let's say 0.1 photon per pulse? Right. What does it mean that 0.1 photons per pulse? Effectively, what I'm doing is, if I think of my light as pulses, let's say a stream of pulses like this. Sorry, that stream is not regular. If you have, how many photons will be there in a pulse? If it's a 1 milliwatt average power, how many photons are there in that? If it's, it depends on the pulse width. If the pulse is, let's say, 100 picoseconds, how many photons would be there? 1 milliwatt will roughly correspond to 10 power 15 photons. So basically 100 picoseconds will give you roughly 10 power 3 photons per pulse, right? So a large number of photons are there in each pulse. If I now attenuate it, I'll essentially get lesser number of photons. And I have to attenuate it to such a level. So I have to have a source which is pulse source. And then I have to attenuate it, right? 100 picoseconds, 10 power 5. Okay, 10 power 5, sorry. Yeah, 10 power 5. Okay. Okay, 10 power 5. All right. 1 picosecond is, yeah. So essentially, you start with a source and you make a pulse laser out of it and then attenuate it. Okay. If you are able to do that, you can actually reduce the number of photons. We reduce it to such a level that eventually, if it's a 1 photon per pulse, you understand what it is. If it's a 0.1 photons, effectively, you send 1 photon in every 10 pulses. So most of the time, you don't send a photon. So essentially, you are generating a single photon, you are sending it.
But which pulse it will be?
It's going to be decided by the random number generator. Which pulse is generating, which pulse has the photon is decided by the random number generator. Okay, I mean, there's even one more step to it. On an average, you have one photon per, well, yeah. That's why, yeah, it's a difficult process. Okay, so now you do this, and then you send these pulses across a channel, and then you detect it. And there are some ways to actually introduce randomness into this. Okay, so if I go here, let me, yeah. So one of the this is something that's already being done. Okay, so one such implementation is what is shown here. So basically what we are doing here is, this is a quantum key distribution hardware. People have done experiments for the last 20 years or 25 years and so on. What they have shown is, let's say you have a laser externally, you use an intensity modulator to generate a train of pulses like this. And then you also, because you have a random number generator that gives you this, you introduce a phase shift. The details are not really necessary right now, but you can introduce a phase shift into those pulses and then finally attenuate it, and you can actually generate less than 1 photon per pulse, and you send that into your transmit into the channel. And then on the other side, you can actually, you need something called as a, this is, the process that I'm describing here is known as DPS, differential phase shift. You are essentially encoding your information as a phase shift, difference in the phase shift. So one pulse, let's say you introduce either a 0 or a pi phase shift in the pulses, so that the difference in that is essentially your encoding, right? Differential phase shift protocol. So you receive that, and then you try to figure out in such a way that if, let's say, if there is a pi phase shift, one detector will click. If it's a 0 phase shift, the other detector will click. So from that, you can know whether it's a 0 or a pi, and that is truly random. So and also it's a nearly single photon source. Okay, and this is also, this is called actually a weak coherent pulse source, because generating of single photons itself is a very hard problem. You could say, oh, I'll simply have a quantum dot or an atom, two-level system, I'll pump it, it'll emit a photon. Well, when it emits a photon, it's a problem. And also, it becomes very difficult to actually control the single atoms. So generally we use an atomic cloud, and there are ways by which we can actually predict when a photon will come. There are Raman transitions that people use, and then try to, in a way, when you get a Raman photon out, you know that, okay, the pulse photon is going to emit. There are ways to actually predict. They're called as heralded photons. Anyway, so you can deterministically control that. And once you have it, and then it's a difficult process actually. So here what we are doing is we are simply attenuating the pulses down. So and why do we say coherent? Well, because there is a fixed phase difference between different pulses. So that's called coherence. And the number of photons is less. So weak coherent pulse source is what we are talking about. And then you can actually show that this is secure. Okay. A lot of work has gone in this area in the last 15-20 years. All right. So, and of course, there are a lot of intricacies into this. This is not a simple thing. See, people have been doing it in bulk optics cases, but even a small vibration, right? For example, I talked about a delay line. Here it's on a chip. How do we build an waveguide on a chip? There's a lot of integrated photonics that is there, and there are courses on NPTEL which actually talk about integrated photonic circuit design, and there are different components. For example, from IIT Madras, from IIC, and so on. There are people who are working on this. If you take those courses, you will understand what this is about. But yeah, so you can build these things. Now, why should we build it on an integrated platform? Why should we miniaturize and build it on an integrated platform? Well, we know from our electronics experience that once the system gets on the chip, it gets more robust, it gets more reliable. So we would like to exploit that, isn't it? So it always makes sense to do that. Okay. So exploit the miniaturization. So we can actually, if you exploit the miniaturization, we make it more robust. We minimize the defects. We can multiplex. So all the benefits that you can gain out of it. Yeah.
What is the distance of the kind of distances they've seen in this kind of transmitter receiver?
Okay, the question was what are the sort of distances that they are talking about in this transmitter receiver configuration? Well, that's a difficult part right now. The reason is you are attenuating the pulse so much, and there is optical loss in the fiber. And the loss is basically 0.2 dB per kilometer at 1550. Okay, so if you have a long fiber, essentially you are losing the photons. So the efficiency of this transmitter system is going to be dependent on the distance. Now, how do we handle that? So people are talking about what are known as quantum repeaters, so that you keep propagating. And also, we are not really looking at for mass deployment. We are looking at for highly secure communications. And if you are able to generate, let's say, 1 million keys and send it, you can have 1 million bursts of information. So these are still things in progress. All right, and probably there can be algorithmic levels of actually handling that. At least so right now we are able to send, I think, kilobits per second kind of time scales over 200 kilometers. That's the distance over which we are able to send. We can't right now send from here to America. That's 10,000 kilometers, and the loss itself will kill it. The problem is if you read it, you are itself you are acting like an Eve if you are repeating. How do we, without we said that Eve actually, once Eve reaches the quantum state, it collapses, and then it cannot it's different. It's introduced an error. So now if you want to have a repeater, how will that work? A quantum repeater is so how do we read it and send it again without actually interfering with it? It seems like we are actually violating the basic postulates of quantum mechanics. So lot of interesting things. It's not known. We are I really think that we are actually trying to read into the mind of nature. I was thinking mind of God, but that seems very presumptuous. So very, very deep things. Okay. So this is what we are right now trying to do. Rather, in the sense, photonic integrated circuits are actually coming up right now. They are commercially available. Toshiba is working on it. A couple of other Indian startups are working on it. So there are ID Quantic and so many other companies which are looking at it. So so this is where we are at right now. All right. So So in the course, essentially, what I've tried to give you was, we have, over the time, last 12 weeks, we have introduced the basic concepts, what electromagnetic waves are, what are the challenges in miniaturization. We talked about how the materials behave, the properties and so on, and then how do we, different approaches to miniaturization. We talked about plasmonics and so on, and periodic potentials, metasurfaces, lasers, nano lasers, and then quantized light and so on, right? We have done all of that. So we have covered a vast range of topics in this entire 12 weeks. Okay. And at times you might actually feel that, it is an overload. And I somehow think that, this is, there is always this entry barrier. Whenever we are working in some areas, especially if they are frontier areas, we don't have, textbooks which people have spent years and decades and tried to simplify it and then give it to you in a small, nugget fashion. We don't have that. We don't have the luxury if you are working at the forefront. If you are not, you don't mind. Okay. See, it's okay for you. It's like, for example, if I think about power transmission, most of the things are sorted out, right? You can just learn it, and the number of open problems in that would be smaller. But here the number of open problems is large. There are no textbooks. And we still have to learn. And if you want to work in those areas, we have to be at that level. Okay. So it's hard. That way I feel that in these things we cannot make it slow. And I also, I think the course was designed to be a postgraduate course. It's not meant to be teaching you everything. You're not, it's supposed to expose you. Provided you're interested, it will take you 6 months to 1 year to keep going back and forth into it and keep learning again, revisiting multiple times so that you get the insight. My job is not to really teach or make sure that you understand. There's a difference between an undergraduate and a postgraduate level. So undergraduate level, your teacher is responsible, or rather in a school, maybe teacher is responsible whether you do it or not. In undergraduate, it becomes lecturer. They'll just talk and you listen or not. It's up to you. A postgraduate level is almost like even more different. A professor is supposed to talk about the subject in a broader sense. Okay, he's supposed to add an insight into the subject, and that's what I have tried to do in this course. Okay, so at times it might feel heavy, but I think you'll have to bear with that. Okay. So, now this brings me back to the beginning. Okay, the beginning I showed you this. I said, there is this classical optics, which, over the last 20 years we have come to nanophotonics. And there's also classical optics which has come to the realm of quantum photonics. The future is, I believe, in the quantum nanophotonics. And in that domain, I think there are a lot of work. Of course, I'm not talking about all the details of what type of work is being done. Okay, but I believe I have given you a foundation to understand this. Okay, so broadly, there are three aspects to quantum nanophotonics: the generation of quantum light, the manipulation of quantum light, and the detection of quantum light. These are the three main domains. Okay, so in each of them, there are innumerable challenges. Just think, I was talking about the quantum key distribution. We have learned that the detector efficiency is very important. Right? If quantum efficiency of a detector is not good, then the quantum light itself becomes non-classical, classical rather. There's too much of noise, right? Rather, the statistics become super Bosonian because of the detection process. So the efficient detectors are actually in the range of visible and near IR, but the channel loss is minimum in the in the near IR, 1.55 microns. Okay, so there's a mismatch in the detectors. There's sources are not very strong, very highly efficient. So we need a very strong, bright source of single photons. How do we design that? If you want a truly single photon source like a nitrogen vacancy or something, it's very, very weak. It cannot be controlled easily, right? How do we make an emission more stronger? Maybe put a nano resonator there, which is high Q. So it actually makes the spontaneous emission faster, so the radiation rate will actually improve, right? Or how do we manipulate photons? We have talked about quantum states of photons. Can we make the quantum states interfere and give you non-trivial results? Can we implement quantum operations, quantum gates? Essentially, logic gate gives you 0 and 1. Let's say AND gate will give you something, a truth table. But what is the analogy? How can I make quantum states interfere and give me an output? There are various quantum states that are discussed in the literature. How do we implement that? Okay, and how do we detect these photons, right? And generate, for example, in generation also we talked about spontaneous down conversion, parametric down conversion, but that's a very weak process. Can I make SPDC stronger? Again, use a cavity to enhance the nonlinearities. Enhance nonlinearities, it will also help you in mixing the states and so on. So this is a very, very broad subject. You can get immersed in it for decades and still discover new things. Okay, so I hope that I have conveyed this sense of wonder and excitement in the area of quantum photonics. Okay, we have not covered many different things still. Now, we have not talked about quantum interference, we have not talked about quantum entanglement, so we have not talked about quantum sensing. So all of these are like buzzwords. Okay, this probably, these things will herald the next quantum revolution, and if that comes out, then the scope is endless. Okay, see, you could not have imagined what happens in 2022 if you are sitting in 1960s. There's been a great revolution in information technology because of computers, and quantum computers are much more powerful. If somebody makes it, the world will change. Okay, so yeah, we'll have to come up to that. So that way, the amount of time, this is all knowledge that is distilled over generations, right? And we don't have generations to learn it. So we'll have to sometimes learn it fast. All right. So that's been my effort. So I hope I didn't really, it was a broad summary that I gave you. Okay. If you have any questions, please feel free to write to me. Mention this course. I will definitely respond. Okay. I'm looking forward to interacting with as many of you as possible. Okay. So we will also try to offer this course next time. So if your friends are interested, we'll have more interactions and so on. So yeah, I'm looking forward to interacting with some of you. All right. Thank you so much. Take care. Bye.